Kirsten Eisenträger with her second talk today. And after this talk, we'll do a 5-minute break, stretch our legs, and then we'll have the final talk by Travis Scholl, which will be a 30-minute talk. So Kirsten will tell us about existentially and universally definable subsets of global fields.
Thank you, Clay. Yeah, so in the second talk, I would like to speak about some recent work from last year and this year, and sort of still with the theme of how close can you get to proving undecidability for Hilbert's 10th problem over Z. So let me just recall that problem. Recall the problem over Z, and so I want to still look at Hilbert's 10th problem over Q and see what we can say about that. So the original problem was find an algorithm that decides, given a multivariate polynomial equation f of x1 through xn equals 0 with coefficients in Z, whether it has a solution with x1 through xn in Z. And so in my first talk, I mentioned that Davis, Putnam, Robinson, and Matiyasevich showed that no such algorithm exists, and that Hilbert's 10th problem is undecidable. And so now I want to look again at generalizations. And so the big open question is, how about Hilbert's 10th problem over Q? So most people seem to believe that it's undecidable, and the nicest thing would be, so if we could just use the proposition that I proved in the morning, or theorem. So that was, if Z is diophantine over Q, then we've seen, then Hilbert's 10th problem is undecidable if Q admits the diophantine model of Z, then it's also undecidable. So in the morning talk, I sort of said that we haven't really been able to get anywhere when we try to construct diophantine models of the integers or an actual diophantine definition of the integers over Q. But sort of would we think that such a result is even possible? And so it seems out of reach at this point to do this, but it's also connected to a conjecture by Mazur And this is a conjecture he made a while ago in a paper called The Topology of Rational Points. And so the conjecture says the following. So let V be a variety over Q. And we're going to just look at the topological closure just in the real topology. And the claim is, or the conjecture is, that the topological closure of V of Q in V of R has only finitely many connected components. And now it's not hard to see that if one had a bunch of equations that cut out the integers, that would give rise to a variety over Q whose closure will be infinitely many components just because of the way the integers are. So that means, so you can actually show as a consequence of Mazur's conjecture so if the conjecture holds, there is no diophantine definition of Z over Q. And it's also not hard to see that there can't be a diophantine model either. So now the question is, do we believe in Mazur's conjecture? So he actually listed this as a conjecture in his paper. This specific version, there are also p-adic versions of the conjecture, and that he himself did not make, but sort of the p-adic analog of Mazur's conjecture in various other settings. And for a bunch of those, Poonen, Schlappentock, and I in sort of various different works have shown that those do not hold. But the original conjecture still stands, and I think it's true for curves. So, but it's sort of unclear. I think I've talked to him a couple years ago and asked Mazur if he believes in his own conjecture, if he believes it should be true or not. And I don't think he had a very strong answer one way or the other. But but if you believe in this conjecture, then this sort of approach would not work. So now we're getting again sort of to the point where, well, when a problem seems very hard, maybe you need to change the problem slightly. So in the morning I talked about getting undecidability not for all of Q, but for getting it for very big subrings of Q. So that was one way in which we could change the problem. We just changed the ring, and we didn't invert all the primes. We just left out some infinite density zero subset of primes that we did not invert. Now we could look at this theorem here and say, well, what's a diophantine definition? It's a definition of the form X is the set of all points for which there exist y1 through ym that make the polynomial 0. So that means I have a bunch of equations and I'm only allowing existential quantifiers because I'm asking for a solution in the form of exists y1 through ym. Now I could just say, well, if I don't know if Z is diophantine, or equivalently, some people use the word existentially definable because are these existential quantifiers only, I could say, well, what if I relax this notion and just allow myself a few more quantifiers? Namely, I could also just say, well, I'll also allow universal quantifiers. Can I define Z then inside Q? And so let me just, and that would be another way of trying to get as close to defining Z in Q as one could, Z in Q as one could, by sort of saying, what is the simplest definition that Z has inside Q if I'm allowing additional quantifiers? So let me sum this up. So in a diophantine definition, we only have existential quantifiers. And so the prototype was the definition of the integers, right? So x is a non-negative integer. The definition of the natural numbers. X is a non-negative integer if and only if there exists x1 through x4 in Z, or I guess y1 squared plus y4 squared minus x is 0. So that was the condition. Now I can also consider what I would call, or what people call, first order definitions. Of Z in Q. And it turns out that this is a problem that has been studied for a long time. And the first result was by Julia Robinson from 1949. And she gave such a definition. And it was of the form, for all, a bunch of quantifiers, there exists then a bunch of variables, for all, and then a bunch of variables, and then came the polynomial. So here, if we're like sort of now trying to get close to an existential definition, we would like this to be as simple as possible, meaning very few changes of types, very few changes between universal and existential quantifiers. So people didn't look at this for a while. And then Bjorn Poonen in 2009 gave a formula of the form for all exists. So that was one that only had one change of quantifiers. Well, and now if you believe in Mazur's conjecture, then what Jochen Koenigsmann did in 2016 is optimal because he gave one that only uses universal quantifiers. So the result is a few years older than this, but the Annals published it in 2016, and I think they have a several-year process. So I think I've seen him give talks on this already in 2012, but so in 2016 it was finally published. And so that means, so of course this is going to be, so there's going to be a negation here, but so he has a for all, then a bunch of variables, and then f for all x1 through xn, the polynomial f evaluated at some number x1 through xn is not equal to 0 exactly when a is an integer. So he has something of that form. So it only uses universal quantifiers, and so that is the universally definable from my title. And so existentially definable sets would be ones that only use existential quantifiers, and universally definable sets would be ones that only use universal quantifiers. So that was his result.
There's negation involved, so usually I'm thinking that you don't allow negations because you can switch your quantifiers. So what Koenigsmann proves is that the complement of the integers is diophantine?
Yes, exactly. So equivalently, what he proved is that the complement of Z in Q is diophantine. Yes. Yeah, that's exactly that. Yeah, another way of phrasing it.
Bjorn and Julie Robinson, there aren't any negations, or are there?
No, so here you don't need the negations.
Okay.
But here, so here you're gonna have it. Yeah. Okay, so basically, what can we do with this? And so what's the goal next after this result? And what's also the goal for this talk then? Well, the DPRM theorem allowed us to completely classify what diophantine sets are over the integers. They're just the RE sets, and it's much easier to check that something is RE than what something is diophantine. So the goal now is, so how can we understand diophantine subsets of Q and global fields better? So to sort of get some insight of what's diophantine and what isn't. And sort of also look at the analog of Koenigsmann's result of defining Z and Q and generalize this to function fields and global fields in general. So let's say global function fields here. And so I will say in a minute what the exact statement is. And so just as a reminder, if we talk about global fields, we have two sets of fields, two types of fields that we're thinking about. On the one hand, there are the number fields, the finite extensions of Q. And then on the other hand, we have function fields over FQ, where FQ is the finite field with Q elements. And so that just means finite extensions of FQT. And I will refer to this second set as global function fields. Yeah, and so that is what I mean when I'm talking about global function fields. And so one question, if we want to understand diophantine sets in global fields, so what kind of sets could we try to prove are diophantine? Well, for example, we could try and prove that the complement of some sets that are obviously diophantine is also diophantine. So there's no reason a priori from the definition why the complement of a diophantine set should again be diophantine. But so that's sort of a natural place to start. And so let's look at complements of diophantine sets. And see if they're diophantine. And so there are two examples, or sort of two natural examples that I want to consider. One is the set of squares, so two examples of sets that are diophantine whose complement I want to consider. So the first set is the squares That's of course diophantine, so that's just the set of all x in Q such that there exists a y. X minus y squared is 0. And so I can ask, squares are clearly diophantine, are non-squares diophantine as well? So that's a question I want to answer. And then I want to do the same thing with non-norms. So for now, let me just look at quadratic norms. So I'm going to take an element y in Q cross. I'm not going to worry right now about whether it's already a square or not. And I'm just going to set f to be Q adjoint root y. And I'm going to just consider the norm map from f down to q that just sends a plus by b root y to a squared minus b squared y. And so this, the image of the norm map, which is a subset of Q, that's certainly diophantine. Over Q. And so what I want to do now is look at the complements of the sets in A and in B. And so in joint work with my student Travis Morrison, we've proved the following. So that if K is a global field, whose characteristic is not 2, and then you can prove that the set of pairs of all xy in K cross K cross such that x is not a norm of K root y is diophantine over K. We're also going to give a new proof of the following theorem by Poonen, that the same holds for the non-squares. So let me just say, as before, let K be a global field of odd characteristic. Then the set of non-squares, so K cross minus K cross squared, is diophantine, i.e. the set of non-squares. That's diophantine over K. So Poonen proved this result using results on the Brauer-Manin obstruction. And so it involves quite a bit of machinery. And so we have a completely different and well, you have to pick your poison if you prefer class field theory and quaternion algebra, or if you like the Brauer-Manin obstruction better. So well, I've talked to someone who works on the Brauer-Manin obstruction, so maybe they find that easier. So different proof from Poonen's proof for non-squares. used results on the Brauer-Manin obstruction. So this is for theorem 2. So these are two results about complements, and then we can also show that the analog of Koenigsmann's theorem holds in, so still 2017, holds in global function fields. So let K be a global function field. Of odd characteristic, we'll have to define what we mean by the analog of the ring of integers. So we're going to take a finite set of primes and we're going to say that the ring of S integers OS has a universal. We proved that that has a universal definition. In K. And so here OS, it's just everything in K who is associated so that the valuation associated to some place P is greater than or equal to 0 for all P that are not in S. So that means we're just allowing poles at the stuff in S. And so so what does this look like? Well, maybe we're not thinking about function fields every day. So what does this actually look like? So e.g., so when my function field is just the rational function field over FQ, so just fractions of polynomials with coefficients in T, then, well, my S has to always be non-empty here to get something non-trivial. So let's say S is just the place that comes from 1 over T. That corresponds to the valuation that just takes minus the degree if I do take the valuation of a polynomial, and then I can just extend it to the fraction field from there. And in this case, what I get is, so when I have my valuation is 1 over T, I'm only allowing poles at infinity. So that means, so what objects have only poles at infinity? Polynomials. So that means in this case, my ring of OS integers is just polynomials in T with coefficients in FQ. And so what the theorem says is that you can define polynomial rings inside their field of fractions with just the universal formula. That's sort of the most basic case of the theorem, but you can do it in all function fields over finite fields with any finite set S. And so this sort of is the generalization of Koenigsmann to function fields. And there's also a generalization to number fields that was done already, and that was done by Jennifer Park. So theorem 3 generalizes Koenigsmann, who did it for Q, and work of Jennifer Park, who did it for number fields. And so now that we have all of these, so now that we have the universal quantifiers, usually number theorists get a little bit more uncomfortable because it's sort of starting to look more logic-y. Sort of when we just have the diophantine sets, it's like, okay, we're just like looking at defining polynomials here. But it turns out that the proof is just pure number theory. So let me just give like a little bit of the flavor of the ideas that go into this. So one of the things that I really like about working on the subject is that sort of different types of fields or rings use completely different methods. So what I was talking about this morning, these subrings of the rationals, were all some elliptic curve, tricky elliptic curve argument. Here, this is going to have a lot to do with understanding quaternion algebras and Hilbert symbol and sort of doing class field theory both over number theory and function fields. So it's like a completely different set of tools that's used here. So let me say a little bit about what shows up in the proof. So I have these three theorems. The machinery that goes into them is all sort of the same, but the most challenging one is the first one. So let me just talk a little bit about that. So overview, even the word overview should be put in quotation marks because it's really just a very brief overview of the proof of theorem 1 for non-norms. And so I'm going to need a little bit of definitions and facts about quaternion algebras and the Hilbert symbol. So let me set that up. Okay, so I'll have a global field K. Characteristic as in all my theorems, not 2. And I'm going to be looking at A and B in K cross. And I'm going to define the quaternion algebra HAB, which is just K plus K alpha plus K beta plus K alpha beta, direct sum. And so this is going to be a quaternion algebra over K. And so what are these alphas and betas? Well, alpha squared is supposed to be A. Beta squared, it's supposed to be B, is going to be B. And then in order to, the only thing I have to say now is how alpha and beta interact. And so alpha times beta is equal to minus beta alpha. And I think we're all familiar with the Hamiltonians, which in this notation would just be H minus 1 minus 1. And so we've either looked at them over R or over Q or something. And so and so there we usually have I and J. And so that I squared equals J squared equals minus 1. And that we have the anti-commuting relations that I times J is minus Ji. So the same setup works here. And now I know that from class field theory or from Brauer groups, of the statement about the exact sequence involving the Brauer group of a global field is equivalent to class field theory. But I know that each of these quaternion algebras, when I tensor with QP, I get in almost all cases just the 2x2 matrix ring over QP. So this is a 4-dimensional algebra. So I get in almost all cases a 2 by 2 matrix ring, and in finitely many cases I get something that's not a matrix ring, and those finitely many places I will say are the places where the quaternion algebra ramifies. So I have this set delta AB where this quaternion algebra ramifies. So that's the places or primes, I'll use those interchangeably, where when I take the quaternion algebra and tensor over K with the completion at P, and that is not the 2 by 2 matrix ring over the completion. So this is the finite set of primes where HAB ramifies. And probably many of you have seen a definition of the Hilbert symbol, but I can also just give an ad hoc definition here. So I have for each place P, each prime P, I have a Hilbert symbol. And so one possible definition is that I'll say that the Hilbert symbol with respect to the prime P is 1 if HAB splits at P, so, and that means that it is a matrix ring. And I'm going to say that the Hilbert symbol is -1 if HAB ramifies at P. So I have the symbol, it takes values plus and -1. And now, so what is the thing that the squares in the quadratic norms have in common over global fields? Well, there is a local global principle for both. And that is sort of what we're exploiting here. So for squares, we can use the Hasse-Minkowski theorem. And for quadratic norms, we can use the Hasse-Norm theorem. So So the main ideas for theorem 1 are then first, we want to use the Hasse-Norm theorem so let me just recall so here I only need the theorem for quadratic norms. It holds in general, more generally for cyclic extensions, but an element X of K cross is a global norm, the one that we're interested in, of a quadratic extension. So this is a special, I should really say special case of the Hasse-Norm theorem. If and only if it is a local norm at every place. And so what we can show now is the following, that X is not a norm of this quadratic extension k root y exactly when, well, so this is just, so this is not yet the Ken show, this is just the Hasse norm principle. There exists a place P such that X is not a norm when I complete. And so here we can show, and that's not hard to see, there exists a P. That's the same as demanding that there's a P such that the Hilbert symbol of X and Y with respect to P is -1. So that means I have now, so in this first step, reduced showing that something is not a norm to showing that one of these local Hilbert symbols, at least one of those, should have the value -1. And now the second step is that there are actually explicit formulas for computing the Hilbert symbol. So this is already in Serre's local fields, so we can compute the Hilbert symbol. And we need to prove some extensions of this, but this is very possible. So we can compute the Hilbert symbol using local conditions on X and Y. And when I say local conditions, I mean you have some prescription of like the p-adic valuation of X should be odd, and some conditions on how the p-adic valuations of Y and X over Y, how they interact. So that's what, yes?
I remember you mentioning that the primes are diophantine the integers, but are the primes existentially definable in the rationals too? It seems like you're quantifying it over the primes or over the places in more generality. So when you do that, but you're working in K?
Right, so I am not saying that this is automatically diophantine. I am just saying right now that if I want to check that something is not a norm, I'm going to have to say that the p-adic valuation of it with respect to something is going to be odd or negative or something. And the key thing there is going to be that I can, with a diophantine definition, define these valuation rings. So, but you're right that the whole thing about how you quantify over all of these is a whole nother story. Yeah, still, yeah. But so I have this local condition, but now, so Marty already mentioned one problem, and so and sort of this is part of like a bigger problem, namely that K has, of course, infinitely many places. But in my diophantine definition, I'm supposed to have like a finite set of conditions that all these guys are supposed to satisfy. So somehow I need to sort of lump the places into groups and sort of find one condition that sort of describes that X, that this is equal, the Hilbert symbol here is -1 for all P in one of the sets in the partition. And so that's where I'm going to use class field theory, and I'm going to use some partition of the primes by looking at the image under a certain Artin map of an abelian extension that I construct. So K has infinitely many places. But in a diophantine definition, I'm really only allowed to check finitely many conditions. So the solution to this is So construct an abelian extension of K of degree 4. It's just going to be biquadratic with Galois group Z2 cross Z2. And I'm just going to partition the primes, at least the ones that don't ramify, into what their image is under the Artin map. The Artin map for this extension. And I'm going to, so that means, so my Artin map is going to land in the Galois group of this extension. So it's going to land in Z2 cross Z2. And so that means I have 4 possible images, and then I want to find one set of conditions for each of these 4 sets. And so in particular, what I need is, so I need to construct, let's call the field L. So A and B are going to have to satisfy a bunch of conditions. And so in particular, so what I want to know is that the splitting behavior of the primes is somehow related to the Hilbert symbol. And so let me just write down what the setup is, and then I'll actually write down the condition for one of these classes. So I have this biquadratic extension L that I constructed with various properties. So I'm going to identify the Galois group of L over K with plus minus 1 cross plus minus 1. So, and then if I have an unramified prime, I can look at its Artin map. Which is basically just the associated Frobenius endomorphism in the Galois group of L over K. And so that means the image under the Artin map for each of these primes is either 1, 1, minus 1, minus 1, 1, minus 1, or minus 1, 1. And I'm claiming that I can come up with 4 different sets of conditions that describes exactly when something is, for all of the primes in the set, whether or not something is a norm or a non-norm in the set. So let me write down what the condition is, just to give you a flavor of what ends up happening. So here is an example. It's really a theorem. So how do I encode failure to be a norm at 1/4 of the primes? And so I'm just going to pick by 1/4. I just mean one of the classes in here. So that means, so I'm going to pick the class -1, -1. And the theorem that we proved in this paper is the following. So there exists a prime P of k such that the Artin symbol takes the value -1, -1. And xyp is also -1. So this said x is not a norm of k root y. And so this happens if and only if so this is what we want for all of the 4 possibilities. So connected with an ORs or something like that. And so here is what one of these conditions looks like. So if and only if, let me start on the next part of the board here. So there exists an element, and so this is not necessary. The whole point is that this is now not going to be a prime, but just an element in the number field. So you have, even though it is suggestively named P, this is just, there exists a P in K, such that P is in a certain set, capital Phi -1, -1. So this is just some diophantine set. And I want x, which I'm checking whether it's a non-norm. I want that to be in P times k cross squared times the intersection of all local rings OP, where P ranges over these delta sets that I defined. And y, or minus xy, is in A times k cross squared, where A is the element that defined this biquadratic extension. And I'm again and so, okay, so this is what the definition looks like. And the whole point now is that everything that appears in this definition, so these are various valuation rings at the prime P, and those can be shown to be diophantine. And so this whole right-hand side is a conjunction of things that are all diophantine, and then I basically have to redo this for the other 3 elements in the Galois group. And since every prime has imaged one of these 4 elements, I then get a set of 4 conditions that then locally describe at each prime whether or not it is a non-norm. And so I can put those together to prove the theorem. Now, the last thing I want to say is I wanted to say that, so right now we're only doing this for quadratic non-norms. And because we have quadratic extensions, we can work with quaternion algebras, which is something that has been studied quite a bit. I already did this in my thesis in 2003. Bjorn Poonen also used quaternion algebras in his first generalization of this definition of Z in Q. And Koenigsmann used quaternion algebras heavily. So, and if you want to generalize it to from non-quadratic norms to higher non-norms, you're going to have to use cyclic algebras rather than quaternion algebras, and there's like a lot more technical difficulties involved. But my student Travis Morrison, in just a paper by himself that he recently posted on the archive, did this for the extended this theorem 1 to cyclic non-norms with some small technical assumption. Yeah. And so I think I'm going to stop here. Thank you very much for your attention. Yes?
So I'm trying to get a handle on how this theorem is proved, because, see, so basically you've got a quaternion algebra that you want to show as a division algebra, and you've got like a twisted P1, it's like Brauer-Manin variety, that acquires a point over L. And you want to, so is there some geometry of this variety that you're picking up with this phi? Like there's something hiding behind the capital Phi. I'm trying to guess what it is. Like,
yeah,
something.
I don't know if I have some sort of geometric intuition. I mean, the way it's worked out right now is just with algebraic conditions. It would be great if there's some sort of geometric conditions that sort of explains what's going on. If there's some underlying geometry going on there, that would be very nice. But so I don't have that view of it right now. Yes?
So with knowing if it's diophantine or not, how been proving it's non-trivial in the Brauer group of this field?
That what is non-trivial in the Brauer group?
The Hilbert symbol.
Well, the Hilbert symbol is just going to be plus minus 1. Do you mean like the HAB or something like that? Well, the HAB, do you mean the Brauer group of the local field or the? Well, so you do want to, so basically what you end up doing is you're going to construct a couple of different algebras so that the intersection of their ramification points is exactly 1 prime p. So you're making sure that you have that you have two elements that are non-trivial in the Brauer group at the same prime p, and otherwise you have like sort of disjointness. So you sort of, what you need to construct are A, B, C, D, such that delta A, B intersect delta C, D is sort of the singleton p. That's the kind of thing you need to work with to sort of get a hold of each prime and sort of and to prove some statement like this. Yeah, but I'm sort of, I have to suppress a lot of things here, unfortunately, in terms of I don't want to, introduce too much notation here. Yeah. Yes?
So kind of into this question before, do we know whether the primes are diophantine in Q?
No, we don't.
No.
So you can't quantify over the primes.
But it's unknown, but is it expected? Like, so if we believe Mazur's conjecture, then Z is not diophantine in Q. But that doesn't necessarily mean that the primes aren't. It's conceivable one could, I guess.
Yeah, I'm not sure. I mean, it seems like a very hard question. I mean, I have no idea how you would think about that. I mean, I think it was also one of the things that, like, immediately when people came up with the result with the conjecture that over Z, RE sets are just diophantine sets. I mean, one argument was immediately, well, then you'd get like these, then the primes would be diophantine, and that wasn't known before. And so those sort of people were wondering if it's really true. And so, I mean, I don't think, I don't have any guess about Q. Yeah.
Any other questions? Okay, let's thank Kirsten again.